Hello everyone, welcome back to a new lesson. We have chapter 4, review and assess. Question 1, it says, what is the relationship between temperature and internal energy? They are directly proportional, meaning if internal energy increases, temperature is going to increase too. We have question 2, it says, what property of two objects determine if they are in a state of thermal equilibrium? If they have, the answer, if they have the same temperature. So remember we studied that thermal equilibrium means two bodies have identical temperatures. Question 3, it says, which drawing in the figure below correctly shows the direction in which the net energy is transferred by heat between an ice cube and the freezer walls when the temperature of both is 10 Celsius. We have the first one, from the ice cube to the freezer wall, no energy transferred, or from the freezer wall to the ice cube, because they have the same temperature. So B is the correct answer because no energy is transferred as the objects both are in thermal equilibrium. A glass of water has a temperature of 8 Celsius. In which situation will more energy be transferred when the air's temperature is 25 or 35? So remember, energy transferred as heat depends on the temperature difference between the two objects. The greater temperature difference, the more energy will be transferred. So when the air's temperature is 35, there will be more energy transferred. How much energy is transferred between a piece of toast and an oven when both are at a temperature of 55 Celsius? Explain. So no heat energy is transferred because they are in thermal equilibrium. Which object in the following pairs has greater total energy, assuming that both objects in each pair are in thermal equilibrium? Explain your reasoning in each case. The first one, a metal knife in thermal equilibrium with a hot griddle. A hot griddle has more internal energy because it has a greater mass. 1 kilogram block of ice or 7 12-gram ice cubes. Which one? Of course, 1 kilogram block of ice because it has more mass. We have question 7. It says, assume that each pair object in question 6 has the same internal energy instead of the same temperature. What item in each pair will have the higher temperature? So for A, we had a knife and a hot griddle. Okay, if they have the same temperature this time, same internal energy, which one will have the higher temperature? Of course, the knife. Okay, a knife. For B, if they have the same internal energy instead of the same temperature, so which one will have the higher temperature? The 7 12 gram of ice cubes. It's basically saying if we give, imagine it like this. If we give the same heat to a knife and a griddle, okay? Because the knife is smaller, of course the temperature of the knife is going to increase faster than the hot griddle, okay? So the one with the smaller mass will reach a higher temperature. Why the steam and ice points of water are better fixed points for a thermometer than the temperature of a human body? Because the temperature of a human body is not stable, but freezing point and boiling point of water are fixed. If question 9, if water in a sealed insulated container is stirred, is its temperature likely to increase slightly, decrease slightly, or stay the same? Explain your answer. It's going to increase slightly because you are making the molecules of the water move faster, and if they move faster, they will be having more kinetic energy, and therefore the temperature is going to slightly increase. Given your answer to question 9, why does stirring a hot cup of coffee cool it down? Well, when you are stirring a cup of coffee, you are making the coffee to be more exposed to the air, okay? So basically it will have more contact area with the air, so it's going to cool it down much faster. Given two bodies, the one with the higher temperature contains more heat. What is wrong with this statement? This sentence is wrong. This statement is wrong because we also have to consider the specific heat capacity and also their mass. Okay, most importantly, we should know if they have a greater mass, because the greater the mass, the more internal energy or the more heat is going to the object is going to have. Use the kinetic theory of atoms and molecules to explain why energy that is transferred always goes from higher temperatures to those at lower temperatures. Well, because the atoms in the object of a higher temperature, that has a higher temperature, are moving much faster. When they came in contact with objects that are at lower temperatures, they're going to transfer some of the energy because of collision, some of the energy to the atoms or molecules in the object with lower temperature, and therefore always energy is transferred from higher to lower temperatures due to collision from the fast-moving molecules to slow-moving molecules. Question 3, in which of the two situations described is more energy transferred? Explain your answer. A cup of hot chocolate with a temperature of 40 Celsius inside a freezer at minus 20 Celsius. B, the same cup of hot chocolate at 90 Celsius in a room at 25 Celsius. The answer is B, because if you just subtract them, you get 65. Here you get 60 Celsius. So because the B has a greater temperature difference, so more energy is going to be transferred. We have question 14. The highest recorded temperature on Earth was 136 Celsius at Aziza, Libya in 1922. Express this temperature in degrees Celsius and Kelvin. So we have Fahrenheit, 136 Fahrenheit. Change this to Celsius and change this to Kelvin. So TF is going to be equal to what? 1.8 TC plus 32. We have Fahrenheit that is equal to 136, which is equal to 1.5 TC plus 32. Move this 32 to the other side, so this becomes 136 minus 32, which is equal to 1.8 TC. This becomes 104, which is equal to 1.8 TC. Divide this by 1.8, divide this by 1.8. Cancels, TC is going to be equal to 57.8 approximately, okay? Now we change this to TC, we change T, so 136 in Fahrenheit is equal to 57.8 Celsius. Let's change that to T Kelvin. So TK is going to be equal to TC plus 273.15. Just plug in the number that you have in T Celsius. So TK is going to be equal to 57.8 plus 273.15. TK is equal to 331 Kelvin, okay? So this is the temperature in Kelvin. We have question 15, the same thing as question 14. Let's solve this one too. We have, let me erase that. We have 1947 Fahrenheit. Change this to Celsius, change this to Kelvin, okay? Same thing. TF is equal to 1.8 TC plus 32. Then 1947 is equal to 1.8 TC plus 32. Move this one to the other side. Then this becomes 1947 minus 32 is equal to 1.8 TC. This is equal to what? This is equal to 15, sorry, is equal to 1.8 TC. So TC is going to be equal to what? Is going to be equal to 1064 Celsius. This is the temperature in Celsius. Let's change that to Kelvin. TK is going to be equal to what? TC plus 273.15. So TK is equal to 1640 plus 273.15. TK will be equal to what? 1337. Okay, this is TK. Same steps basically as question 14. We have question 16. It says a force of 315 Newton. A force of 315 Newton is applied horizontally to a wooden crate in order to displace it 35 meters across a level floor at constant velocity. As a result of this work, the crate's internal energy is increased. So look, it's talking about work. Okay, so we can put this into words. It becomes work is increased by an amount of 14% of the crate's initial internal energy. So we have 14%. Whenever you have percent divided by 100, you get 0.14. Okay, so 0.14 delta U. Okay, this is how much the work has changed to internal energy. Now, we have force. Let's write the givens. F is equal to 315 Newton. We have D, which is equal to 35 meter. Now, I cannot use, just to point out, I cannot use the equation for potential energy. Why? Because it says it is moving horizontally. So we cannot use H because there is no change in the height of the object. It's moving horizontally. Then we have work, which is equal to FD. Then this one is equal to 0.14 delta U. 315 multiplied by 35 is equal to 0.14 delta U. Then this is equal to what? This is equal to 11,025, which is equal to 0.14 delta U. Divide this by 0.14, cancels. Then you have delta U, which is equal to 7.8 times 10 to the power of 4 joules. This is question 16. We have question 17. It says a 0.75 kilogram spike is hammered into a railroad tie. The initial speed of the spike is equal to 3 meters per second. If the tie and the spike together absorb 85% of the spike's initial kinetic energy as internal energy, calculate the increase in the internal energy of the spike. So we have delta U, and before that, let's write mass is equal to 0.75 kilogram. Velocity is equal to 3 meters per second. We had 85%, let's not forget that. So what am I going to use? We're going to say delta U is equal to KE. Why do I use KE? Because we are dealing with velocity. Okay, so delta U is going to be equal to 0.85. Don't forget to divide 85% by 100 times 1/2 mv squared. Okay, so delta U is equal to what? 0.85 times 1/2. Mass is equal to 0.75 times velocity is equal to 3 meters squared. So you should get 2.87 joules. This is the internal energy. We have question, we have B. It says what happens to the remaining energy? So the remaining energy is equal to 15%, which can be transferred to the surrounding air, or it can be transferred to sound. Okay, it can be the energy can be transferred to or converted to sound. What data are required in order to determine the specific heat capacity of an unknown substance by means of calorimetry? So remember, we had Cp of the substance, mass, and change in the temperature of the substance, which was equal to Cp of water times mass of water times delta T. This was the substance side, and this was the water side. Now, if you want to find Cp of this substance, okay, specific heat capacity for the substance, what are you going to need? Well, first of all, you're going to need the mass. This is the answer. What data are required in order to determine the specific heat capacity of an unknown substance? So first, we need mass. We need T initial and T final for the substance, initial temperature and the final temperature, or we can basically say change in the temperature of the substance. We need specific heat capacity for water. We need the mass of the water, and we need change in the temperature of the water, or we need initial temperature of the water or final temperature of the water. So we need 5 things. This one first, this one too, this one, and this one, okay? These are the things that we are going to need to find the specific heat capacity of a substance. What principle permits calorimetry to be used to determine the specific heat capacity of a substance. Explain the conservation of energy principle, okay? Because the heat that is lost by the substance is going to be gained, is going to be absorbed by the water or by the liquid. Okay, this is basically a conservation of energy, or you can say Q lost is equal to Q gained. Let's say 2 joules are lost here, so here 2 joules are going to be gained or absorbed. Why does the temperature of a melting ice not change even though energy has been transferred to as heat? So during a phase change, remember we had latent heat of fusion and latent heat of vaporization. During these phase changes, there's not going to be any temperature change because the energy that is transferred to the substance is going to be used to break down the bonds between the molecules of the substance, okay? Why does evaporation of water cool the air near the water surface? Because when evaporation happens, it's going to absorb the heat from the surrounding air, okay? And therefore, it's going to cool the air near the water surface. 22, ethyl alcohol has about 1/2 the specific heat capacity of water. If equal masses of alcohol and water in separate beakers at the same temperature are supplied with the same amount of energy, which one will have the higher final temperature? So remember, specific heat capacity was the energy needed to change the temperature of a substance. The higher the specific heat capacity, the harder for the object to be heated, or the harder it gets to change the temperature of the object. So water has a really, really high specific heat capacity. Ethyl alcohol has 1/2 of the specific heat capacity of water. So which one is going to have a higher temperature if we give both the same amount of heat? Of course, ethyl alcohol, because it has less specific heat capacity. Until refrigerators were invented, many people stored fruits and vegetables in underground cellars. Why was this more effective than keeping them in the open air? Well, because underground cellars, the temperature there is more stable, and the soil acts as an insulator, okay? So energy is not going to be transferred to the soil or to the underground very easily. During the winter, the people mentioned in item 23 or question 23 would often place an open barrel full of water in the cellar alongside the produce. Explain why this was done and why would it be effective? Well, the water has a very, very specific heat capacity. So it's going to, of course, when it freezes, it's going to release heat, and it's going to keep the temperature of the room in a moderate condition, okay? Most importantly, when water freezes, it takes a lot of time. And even when it freezes, it's going to release heat. This heat is going to be used to keep the temperature of the room. We have question 25 and the last question for this video. During a cold spell, orange growers often spray a mist of water over their trees during the night. What does this accomplish? Same thing as question 24, because water takes too much time to freeze, that's the first thing, and it's going to keep the oranges from frosting, okay? Or it's going to keep the oranges from damage due to frost. So even when water freezes, it's going to release heat. This heat is going to be transferred to the oranges, and they're keeping them in good condition. And this is basically going to slow down the process or keep the oranges intact. This is it for today. See you in the next video. We will be continuing solving the questions from chapter review and assess. See you.